All right. Okay. Any questions before we start? Comments?
Just wondering, are we gonna go over a little bit more on coordinates, or should we do more reading about that?
What do you mean? Could you say a little more? What do you mean about coordinates?
I guess kind of like going between coordinates, or yeah. If not, don't worry, I can read up on it.
Are you thinking of this because of the question on the assignment?
Yeah.
Right. All right. Maybe I'll say a few words about it. But you would have seen this in, for example, vector valued calculus. So when you do what do they call it? Vector calculus, right? That you do a change. For example, the part of the course where you study changes of coordinates and integration. You learn this fact that if you want to do an integral in a different coordinate system, then you need to compute the derivative matrix and then use it for finding the determinant, and then so that kind of material is what I'm referring to here. So you can change your coordinates, and see the other advantage of the Hamiltonian formalism is that it doesn't depend on coordinates. But the problem is that you need to yeah. So let me explain this fact. It is a confusing thing, and it might be useful to go into a little bit more detail about it. Okay, so let me just start with that. So this is an aside on coordinates. In phase space. All right. All right. So the way you should think of coordinates is like this. So we start off with a configuration space. Which has coordinates x1 up to xn. So this is like, for example, in the example that we did, the position of the mass, this coordinate was x. So the position of the mass or of the particle has a certain coordinate, and that is the configuration space. And so if you want to talk about unit vectors or tangent vectors to the configuration space, let me call the configuration space Q. Tangent vectors to Q are given they have a basis given by dx1 up to d by dxn. And then the so-called cotangent vectors have dual basis dx1 up to dxn. So I'm hoping that without going into too much formal mathematical nonsense, this is understandable in the sense that every point has a tangent space. That tangent space is a vector space, and the basis for that vector space are exactly is exactly this d by dx1 up to d by dxn, and that space has a dual space, which is the cotangent space, and you'll have a dual basis. Right. So a general cotangent vector at the point x1 up to xn is a linear combination of the basis of the cotangent space. So is p1 dx1 plus pn dxn. And so this is how we get the so-called conjugate variables. So these are the so-called, these are the momenta variables conjugate to x1 up to xn. Okay, so what I'm trying to say here is that, okay, so these are variables on a different space than the x's. These are variables which parameterize the different dual vectors to a point. So for example, you should think that we have some space Q. We have a point which has coordinates x1 up to xn, and we have a tangent space which has a basis d by dx1 up to d by dxn. And that tangent space has a dual space, which, for lack of a better way of drawing it, you could just think of it as being some dual space here, T star Q. All right, and this space has a basis given by dx1 up to dxn. And a general point in there has coordinates p1, pn in that vector space. All right, so in total, we have two n coordinates. The first n coordinates allow us to move around on the q space, and the rest of the coordinates allow us to move around in the p space. Okay? And in total, we have n plus n directions in which we can move. Okay. Now, the important thing is that you can choose the x coordinates however you want. Okay. So, for example, if you're trying to describe, let's say that you were trying to describe the motion of a pendulum, so you had some fixed location and some string and some mass. And this, this is like a one-dimensional pendulum. And let's say that it's a flat, that this pendulum is in the plane, right? If I needed to choose a coordinate for the position of this pendulum, there's many choices I could make. One of them is, for example, the distance from here to here, which I could call x. Let's say from the vertical line to the vertical, you drop down a vertical line from where the pendulum is, and then you measure the distance from the resting point to this. That could be your coordinate on the configuration space. But another possibility is that you could use, let's say, this angle, theta. That's a perfectly valid coordinate as well. Or, in fact, you could try to use, let's say, the height coordinate. All of these, you can pick one of them, and it will do the job of telling you where the pendulum is. Okay, and so these are all examples of coordinates on configuration space. Okay, they don't need to be rectilinear coordinates or any kind. They can be curvilinear coordinates, as you would call them in the old-fashioned way. And once you've chosen that, then there is a canonically conjugate coordinate system on the cotangent space. There is no choice after that point. So once you've chosen your x, the q's are determined. And they are determined by this formula here, that we're using a dual basis, which is the derivatives or the differentials of the coordinates. So the idea here is that if you make a change of coordinates from the x's to another possible choice of x's, so let me I'll get to your question after, Romain. So the choice, so we may choose. So this would be like weeks would be spent on this in a course on analytical mechanics, but I'm just going to try to do it in 15 minutes. So we may choose our coordinates arbitrarily, but then the p's are determined. So okay, so if we change coordinates, let's say like this, let's say I define some new coordinates x tilde, which are, each of them is a function of the previous coordinate system. So I have n functions. Okay, so I have n new coordinate functions, and so because in my original coordinate system, let's say this was my original coordinate system, x1, x2, right? The new coordinate system could be curvilinear x tilde 1 up to x tilde n. Okay, and the point is that these two new functions, or these n new functions, they are prescribed functions of the previous coordinate system. So the point is here that the vector fields that I'm now using as a basis, they used to be these d by d x1 and d by d x2. But now in the new coordinate system, there's a new basis, and that new basis actually depends on where you happen to be. So what this means is that if you had the, in the original coordinate system, you were using this fixed basis, which was the same no matter where you were, right? But now I have a different coordinate system, and in that coordinate system, there will be a unit basis vectors. But those basis vectors will have to be expressed in terms of the original basis if you want to do this change. So so in principle, we need to express d by d xi tilde, the new basis vector, in terms of d by d x xi. And that's a change of basis. It's a change of basis which depends on the position. Because depending on what position you're at, the derivatives of x tilde I with respect to x will change. Okay. So how do we write this? Well, you would write d by d x tilde I would be, dx by dx tilde d by dx. So, you've seen this type of formula before. The difference is just that we're in n dimensions. So this will be a sum over k. And we're differentiating with respect to x tilde I. Okay. So this would be your change of variables formula, or your change of basis. This would be your change of basis matrix. Okay, and in order to compute it, you would need to solve, it's a little bit annoying because what I'm giving you is the new coordinates as a function of the old ones. But what you need to compute is the partial derivatives of the old coordinate system in terms of the new one. So you need to do some kind of calculations in order to find this change of basis matrix, right? So it can be a little bit of a tricky calculation. But what about the dual basis? The dual basis, I can express it in the following way. All right. So in order to find the dual basis, it's a little bit easier because of the way that it transforms. You see, what I need to know in order to know this dual basis is I need to know the derivatives of x tilde with respect to x. So it's slightly easier to find the dual basis, actually. But then you would need to invert that matrix anyway in order to find the basis for the tangent space. Maybe it may be easier to compute. Okay, and then we have okay. So what? So well, okay. This is important because of the fact that this is the basis that we're using for the p coordinates. So the new the new canonically, okay. So a point in the cotangent space to a certain point x is given by x to figure out which point you're at in the base, and then p. Or in the new coordinate system, so this is in the old coordinate system, or by x tilde 1 up to x tilde n, p tilde 1 up to p tilde n in the new coordinate system. So the question is, how do I figure out, if I know, if we are given x tilde I as a function of x1 up to xn, how to determine p tilde I as a function of the p's, but also of the x's, so that I'll know how to find the canonically conjugate coordinates. Well, okay, for that we just use the definition of the p. So So a point xp refers to the covector p1 dx1 plus pn dxn at the point x1 up to xn. Okay, it's a dual tangent vector to that point. Okay, so and then if I take this thing and so we would like to write this. We want to write this vector as p tilde 1 dx tilde 1 plus p tilde n dx tilde n. We want to write the same point, but in terms of the different bases, and the coefficients will be our new coordinate system for the p's. Okay, so this equation is the key thing that tells us how to, you see, like we have a vector with respect to this basis, we have another vector with respect to this basis, and these p tildes are exactly the thing we want to find. So so you could write it like this. You could say if so if we write p tilde I dx tilde I, if this is supposed to be equal to the sum of pi, or let's say pk dxk, right? And if I can write this dxk in terms of a sum of dxk dx tilde I, let's say p dx tilde p, where p goes from 1 to n, right? Then I'll get that this is a sum of pk. So sorry, this is k is 1 to n, I is 1 to n. And this is going to be pk dxk dx tilde p dx tilde p. So maybe just to simplify notation, I could have used p out here. Sorry, that just in case that is confusing, let me use n. And here n. Okay, so this is telling us that p tilde n is equal to a sum of pk dx dxn. Okay, so you see that the new canonically conjugate variables can be written in terms of the p's and the x's. I just want to make sure that
the first sum you have n equals 1 to n.
Yeah. Oh, I'm sorry. Yeah, sorry. This is not a good idea. M.
And the p's in the third sum are m's, right? Or the same as the m?
I think you understand what I'm saying. I don't want to be pedantic. I'm just trying to explain some elementary facts about change of coordinates. So now, okay, so these formulas are not so important. I mean, the most important thing is the idea that the p's in in this way of thinking about the phase space. I think that the assignment, I don't remember exactly what the assignment question is asking, but the point is that when we write so think of it like this, that we start with the x's, and this we embellish by adding the p's, and from this we can write the Poisson bracket, which has this standard format that it involves differentiation with respect to the p's and the x's, and there's a summation over that. If you make an arbitrary change of coordinates to the x tildes, okay, and when you make that change, you will know the x tildes as a function of the x's. So the relationship between the x's and the x tildes is known. But from this, we automatically get the doubled coordinate system. So we get the p and tildes. Okay, so the p's are a consequence of the x's, and then we can write the Poisson bracket. We can write the Poisson bracket in terms of these x tildes and p tildes using the same formula. So it would also be df by dp I tilde dg by dx tilde I minus the same thing, the same expression. Okay. And the point is that the Poisson bracket is the same in one case and in the other case. Even though you're writing it in terms of two different coordinate systems, the Poisson bracket is the same. The function that you will get, if I put in, if you give me the job of having to compute the Poisson bracket of f and g, then I have to do the following. I have to express f as a function of x and p, and then take the derivatives and combine them according to the what's given. But I could take those functions and express them in terms of these new coordinates, x tilde and p tilde, and compute the bracket using the formula in terms of those x tildes and p tildes. All right, and I will get the same resulting function. So this is the meaning of the statement that the phase space has a natural Poisson bracket on it, which is independent of which coordinate system you happen to choose on your configuration space.
Sorry, just to clarify,
Yeah.
these p's, are they the same as the first lecture where we made m times x dot, or it's a different?
Yes. Yes.
Okay.
Yeah. They are the additional coordinates that you add in order to convert the second order differential equation into a first order one. Okay, Romain, question?
Why do we, so intuitively the p's are the momentum,
Yeah.
which would seem to correspond more to the tangent bundle. Why do we bother with the cotangent bundle? Is it because of these easier computations, or because of the Poisson bracket?
The reason is that the intuition is incorrect. Your intuition that the momenta are tangent vectors is not correct. They're actually dual to tangent vectors. The truth of the matter is that momentum is the answer to a question. The question is, how much momentum is there in this direction? And the answer is a number. How much the momentum is there in this direction? And you get a number. That's the truth of the matter.
That's why the cotangent bundle makes sense.
Yeah. Okay, so let's just look at where we are right now.
Professor?
Yeah.
I have a question. So the naturality of the Poisson bracket,
Yes.
it depends on this particular structure of the fact that you have Q and then you have the cotangent bundle. So if you just have an arbitrary manifold of 2n dimension and then you take it wouldn't work. You
If you
need,
have a manifold of size 2n with 2n variables, okay, there is no there is no natural bracket defined on that space. The
I see.
reason that we have a bracket, the reason why this bracket is well defined, is because of the fact that half of the coordinates depend in a very particular way on the other half. Okay, and that dependence, that relationship, is captured to some extent by the Poisson bracket. Okay,
I see.
Yeah.
Okay, thank you.
The thing is that it isn't like I won't really be able to you have to get used to this idea. It's not the most obvious one, I would say. So okay, okay. So roughly, so just summarizing of what we have so far. In classical mechanics, we have the state is a point in phase space, and the evolution is determined by a function h. So the phase space has x and p coordinates, and this is a function of x and p via the Poisson bracket, and it works like this: that the time derivative of x is given by the vector field determined by the function h acting on x. And the way that p changes is by the vector field determined by the function h. All right, so here, if we work this out, this will be the derivative of h with respect to p times the derivative of x with respect to x minus the derivative of x with respect to p, which is 0. So we just get this. And similarly here, this will give minus dh dx. Okay, so just zooming out, these are Hamilton's equations of motion. Okay, and it's just another way of presenting the fact that on the xp space, on the phase space, we have a vector field, okay, whose which we called v sub h. Okay, and this vector field was exactly determined by the way that the Poisson bracket acts on functions. So you see here, you should think of h as being fixed, and this Poisson bracket of h against x, that's like an operator that is basically saying, it's basically differentiating x in a certain direction, the direction v sub h. But we don't really need to involve this vector field explicitly. We just need to use the Poisson bracket. This Poisson bracket does the job of converting this function into a vector field, which then acts on x. And if we write it explicitly, it's just the derivatives of h with respect to p. So in our previous example, h was the function 1/2 p squared plus x squared, and then dh dp is equal to just p, and dh dx minus dh dx is equal to minus x. Okay, and so we end up with we end up with x dot is equal to p, and p dot is equal to minus x, and that gives us exactly the circular motion of the harmonic oscillator. Okay, so I just want to zoom out from this a little bit and just look at what, in this example, what we're looking at, what we have dealt with. So we have considered three classical observables. Okay, the three observables are the position of the mass, the momentum, and the energy, the total energy. These are all functions on the phase space. Okay, so we've focused our attention on three physical observables, or classical physical observables. Okay, they're quantities that you could in principle measure, right? And we should think of them as functions on the space of states. For every state that the system is in, this function will have a value. The position, it will be in some position, it will have some momentum, it will have some energy, etc. Okay, and I just want to point out that you can interpret Hamilton's equations in two ways. You could think of it as defining the motion of a point, and that you're looking for an integral curve, or you could think of it as something which is dictating the future evolution of a function. You could imagine that this is actually saying that I have a function x, and I want that function to change, right? So you could, we can interpret Hamilton's equations in two ways. I know that I said this last time, but I want to make it a little bit more precise. Okay, in the first way, we think of x and p as a point inside phase space, and we think of it as a motion of a point. The time derivative is dictated by Hamilton's equations. The second way of thinking is that x and p are functions on phase space. Therefore, x and p are actually elements, as well as h. These are elements of the space of functions, which itself is a vector space. Okay, and you could think of this infinite dimensional vector space as being the place where the dynamics happens. It's infinite dimensional, so there's many axes, okay? And we've got this point, which is the function x inside this infinite dimensional space. And you could think of it as describing the motion of this function, right? So you could say that the experimentalist is kind of measuring the position of a mass, and they're saying, well, the mass is 2, the mass is at the point 3, the mass is at the point 4. He's describing, or she's describing, the motion of this point in time, right? And then you could say, well, oh, but how do you know that maybe the mass is not moving at all? What's happening is that the position function is actually being changed in time, right? So, of course, these are equivalent. There's no big difference, but I just want to point out that in one case we're thinking of a point in a two-dimensional space moving, whereas in the other case I'm thinking of a vector in an infinite dimensional space of functions moving. Okay, and these are both of these points of view are they come into play in quantum mechanics as well, as we're going to see later. Okay, now I want to bring up another point about perturbations. And this is related to the assignment. So if we modify our energy to h epsilon, I think this is the same one that I put into the assignment, x squared plus p squared plus epsilon x cubed, where epsilon is some small positive number. So you see, like, because the Hamiltonian formalism is also useful for doing perturbation theory. Now, what do I mean by that? Well, what I mean is, because the entire motion of the system is dictated by this single function, what we could do is we could just perturb it a little bit, the function, and see how the motion changes. And that corresponds with changing the energy. How do we change the energy? Well, we might tweak the strength of the spring, let's say, and we might make it so that when you pull on the spring a certain distance x, that maybe instead of minus kx, instead of the force being minus kx, maybe it could be minus kx, plus epsilon x squared. So in other words, maybe there's a higher order term where the spring is not perfectly linear in its behavior, but maybe it has a higher order correction to its behavior, okay, which depends x on x to the power 2. In principle, that's how it has to be, right? The function has to be some function of x, and we could expand it in Taylor series, and there will be a linear term, and Hooke's law says that that's the dominant term. But there could be higher order terms. So if there's a squared term, that will affect the energy, the potential energy, basically by integrating, and it will show up in the total energy as some higher order term in x. So this is what I mean, that in reality, any spring is really, is if you measure it precisely enough, it will have this this slight small term in x cubed. And then you might say, well, what's going to happen to the motion? Well, the cool thing is that you could just figure out how the level sets are affected, right? So for epsilon equals to 0, the levels, this is just x squared plus p squared. So the level sets are perfect circles, which I can't even draw. Right? But if we modify the function in x and p, then we could just draw its level set. So what would the level sets be for a cubic function like this? Well, they're going to be quite different from level sets of a quadratic function. The level sets are not going to be ellipses anymore. They're not going to be hyperbola or ellipses. They're going to be cubic curves. And a cubic curve, well, if you try to graph this equation, this is a very famous equation. It's like p squared. There's a p squared, so that means that it will be mirror symmetric. It'll be symmetric about the x-axis, right? P goes to minus p as a symmetry, and you also see that if we look at the suppose that we look at the zero level set, right? We can see that the zero level set will go through 0, 0. Oops. But it will also go through, like x has an, for example, if we, so there will be some negative number where x squared plus epsilon x cubed, right? If I look at x squared, let's say 1 plus epsilon x plus p squared, if I rewrite this bracketed term in this way, and if I set p is equal to 0, suppose, then x can be 0, and I'll be on the 0 level set. But if x is minus 1 over epsilon, then this point will also be in the 0 level set. So this is different from the previous case. In the previous case, the 0 level set was just the point at the origin. But here I'm going to have another point, not just the point at the origin. Anyway, so if we work out what the level sets are, it's going to look like this. So there's going to be a fishtail. Like this. And like this. So these are cubic curves. So the interesting thing, what happens is that just by putting a little epsilon there, you can see a lot about how the system is going to change. You can see that if you are doing small oscillations, then we're still going to get things that, roughly speaking, look like ellipses. They're just slight deformations, distortions of an ellipse. But that will persist up to a certain point, and then it will break down completely. And you have this particular value of the energy, that if you put enough energy into the thing, it will be on this singular level set, this level set that crosses itself. And then, well, you can think about, what that means about the motion. But if you put a little bit more energy, then you get this strange behavior where this just goes off, and of course that kind of comes from the fact that for negative values of x, this thing is behaving strangely once it's large enough. So really, what you would like to do is focus your attention for small energy, and you could try to compute, for example, how does the period of revolution, how does the period of the oscillation change with this modification, with this small perturbation. So later on, we're going to do a lot about perturbation theory, and it'll be similar to this, that we're going to want to take the Hamiltonian and make a slight change to it. And that will, just changing that one function basically tells us exactly how the system is modified.
Professor?
Yeah.
Given that the epsilon is very, very small, won't the point -1 over epsilon be like really far away in the distance?
Yeah, that's right. It suddenly appears, but in a place that's very far away. So probably if you're dealing with a physical spring, right, that bad point in phase space, or that interesting point in phase space, is not really accessible from a practical point of view. If epsilon is truly small, -1 over epsilon is extremely far away, which is beyond where you would bend the spring. At some point, if you bend the spring too much, then it'll just break. It'll, you'll overcome the elastic boundary for the material and so on. Okay, so let's look at another example that goes beyond this spherical pendulum. Let's go beyond this simple harmonic oscillator. I want to do two examples which are useful for us to understand. Each of them is going to bring a new kind of idea into the subject. So let me do a second example. It's very close to the first example. Example number 2 will be the following. So let's talk about a system of n oscillators. Okay, and the reason I'm doing this example is because we need to understand how to combine a simple physical system to produce a more complicated one. How do we, attach them together like Lego blocks, to make something larger, a larger structure? So we studied a system which was given by a configuration space R with a phase space R cross R, X and P, phase space. And we also give, we also provide this function, which is 1/2 P squared plus X squared. Okay, and that Hamiltonian is the Hamiltonian which defines the motion of the simple harmonic oscillator in one dimension. Okay, but suppose that we want to consider now R to the n. So we can use this to produce an n-dimensional system of oscillators. And the way that we do this is by saying that, if I have, sorry. So I'm just trying to explain in a way that I'm going to be able to generalize later. So this describes a single oscillator, a single physical system. Now suppose that I have n of them, n independent oscillators. Then how do we go from this to the full system? Well, the configuration space will be a Cartesian product, an n-fold Cartesian product. Okay, because of course it's, a configuration is given just by specifying the individual configurations of each of the n systems, and so we get a Cartesian product. And the phase space will be R to the n cross R to the n dual, in which we have coordinates x1 up to xn and p1 up to pn. All right, and then the Hamiltonian of the system, what's the total energy? It will be the sum of the individual energies. So it will be H1 plus H2 plus Hn. It will be the sum of the total energies of each component.
So just to be clear, like we're assuming that each of these oscillators are one-dimensional oscillators?
Yeah, it's the system that we started with right here. It's this oscillator.
Oh, okay.
We have n copies of this oscillator, all right? And then mathematically what we do is we take the phase space. So the phase space, in other words, is the phase space for the one oscillator, Cartesian product n times. And you see how, this has n projections to M1, right? And what we're doing is we're just taking the function each one of these has a function on it, which is this h. This has a function h. This has a function h. Right? I'll label them. And this has a function which is just the sum of the two of the n functions. So this function is the sum 1/2 xi squared plus pi squared. Okay, so mathematically what you do is you take the Cartesian product of phase spaces, and then you take the sum of the Hamiltonian functions. Okay, this is the rule. This is the law of what do you call it? Of kind of aggregation of a system, of aggregate systems. Okay, and this is really important because, typically, when you're modeling, let's say, a crystal, you think of each atom in the crystal as being an oscillator, not a one-dimensional oscillator, maybe a two or a three-dimensional oscillator, but there's a huge number of these oscillators, and the phase space is the Cartesian product of all these oscillators, of each individual one, right? And then we take the sum of the energies. So the Poisson bracket is also well, okay, so that was contained in what I meant here. So maybe I should specify this here. You're taking the Cartesian product of phase spaces with the product, with a combined Poisson bracket. Remember that the Poisson bracket is already a sum over all of, it's a sum over I of differentiation with respect to xi and pi. And so now we're going to have, because I'm taking the Cartesian product, that means that I'm going to have more and more of these xi's and pi's, and we need to continue that sum. So that's what I mean when I say Cartesian product of phase spaces. We're going to increase the number of x's and p's, and then that's going to have a huge Poisson bracket on that. Now we're going to have a huge Hamiltonian, which is the sum of all the individuals, and we're going to use the big Poisson bracket and the big Hamiltonian to govern the motion of all the of the point in phase space. So the fascinating aspect of this is that we can now add new terms to the Hamiltonian to the resulting h. Let's say we had this, for example, we had this 1/2 sum of xi plus pi squared. We could add a term like, for example, just as an example, we could add a term x1, x2 to this. And notice that this is a completely different type of term because it is not defined on the phase space of the first particle or the second particle. It is not a function only of x1 and p1 or a function of only x2 and p2. It's actually a function on the new phase space, which didn't exist before. It's a function on the Cartesian product, which is not a product function. It's not a function that is made of function, that is a single function on one of the Cartesian factors. So this is not a function of a single phase space. So it is new in the Cartesian product. Right? You can think that when you take the Cartesian product of two spaces, you get a bigger space, and therefore you get more functions. Functions, you get very many more functions that you didn't have before on the individual spaces, right? Originally, you had only functions of x. Let's say, if I take the xy plane, the functions on the xy plane are way more than the functions of x and the functions of y. We get functions like, arbitrary functions of x and y, which are not one-dimensional functions, right? So, so the point is that such a function is called an interaction term. Okay, because it depends upon the state, the joint state of two components of the system. It does not depend only on the state of the first particle or only on the second particle. You see what I mean? It depends on the joint position of the two. And it's precisely that idea which tells you that there's an interaction between the two systems. The only way that you can get an interaction between the two systems is if there's a part of the energy which is dependent on the joint position and joint momentum, right? If the energy was unaffected by the joint positions, and if it was only affected by the individual positions, then the energy wouldn't care about, saying that if this gets closer, right, then, if these two particles, let me put it this way. This way of thinking in phase space with the Hamiltonian function, it basically says that if you want two particles, it's kind of reversed, right? Let me put it in the form of a quotation. If we want two particles to attract each other, that would be a form of interaction. We must design the Hamiltonian function. We must design this special function that governs the behavior of the system. We must design it in such a way that it is reduced when Q1 minus Q2 is small. So, in other words, if you want to build a system, right? If you want to build a system of two particles, right, which are kind of vibrating, so you can start with we can start with this system. This is a good system to start with. The two particles are behaving like individual oscillators, and they're moving like sinusoidally, right? But if you want them now to affect each other, and if you want them to attract each other, then you need it to be so that when they come closer to each other, the energy is reduced, right? Because we want it to be energetically favorable for the particles to be next to each other. That's what it means for them to attract each other. It means that the Hamiltonian function is affected by x1 minus x2, instead of q1 minus q2. So what we could do is we could add a term, let's say epsilon x1 minus x2 squared. I'm sorry, we should subtract a term. So we could do something like this. Sum 1/2 xi plus pi squared. Let's say I is going from 1 to 2. And then I do some small number, epsilon. Epsilon is some small, and you subtract it. Okay. I haven't done any work of figuring out what the system is going to behave like. I have no idea. But I know that it's energetically favorable. I just want to make sure that I'm... Yeah, it's energetically favorable for x1, the distance between x1 and x2, to be less. Sorry, did I make them repel? Can someone see if I've made them repel or not?
I think you've made them repel, because if they're far away, then your term is big, and so your energy is small.
Yeah. So let me put a plus here, and that makes them attract. You see, because this term is always positive, and it's always big when the distance is big. So the only way to make it smaller is to reduce the distance between them. So this, let me put it this way. If epsilon is positive, this would be an attractive force. And if it's negative, it would be a repelling force. Okay. Yeah, question?
Interaction terms might be dependent on our coordinate system, no? Like there could be a way in which we view our system so that we can actually break it up into smaller individual.
I'm going to stop you right away, because the Hamiltonian is a function on phase space. That's what the Hamiltonian is. It is a function on phase space. The coordinates are other functions on phase space. You can have whatever coordinates you like. But the system is determined by the phase space and by the function, the Hamiltonian function. That's it. You can choose whatever coordinates you like, and then the motion of those coordinates will be determined by the Poisson bracket of h with x.
Right, so we don't actually care about the
Coordinates are irrelevant for the definition of the system. They're only relevant for the description of the system. Okay. All right. So, so this is really important, because we're going to have to deal with this in quantum mechanics. In quantum mechanics, we're going to do the same thing. We're going to describe what an individual system is determined by, how to describe mathematically a single system. And then we're going to have to describe how to combine elementary systems to make aggregate systems. And that's going to involve not a Cartesian product, but a tensor product. Okay, now let me do another example, example number 3. And this will be the spherical pendulum. Okay, so what's the spherical pendulum? Spherical pendulum is, let me see if I can I move this? Oh no. Okay, so the spherical pendulum is a fixed point on the ceiling, and I have a pendulum coming down into the room, and this pendulum can move in this direction, but also in this direction, and so really it's moving along an imaginary sphere of radius given by the length of the rope. Okay, and actually let's take this system and make it more abstract. Let's remove the ceiling, and let's extend. Let's extend this imaginary sphere to be all the way around the pendulum. So we have a fixed. You could imagine there's like a little drone here floating in space, and it has a pendulum stuck to it. Okay, so we have a pendulum that is free to move on the two-dimensional sphere. Two-dimensional sphere under gravity. So there's a force of gravity pointing down. So just intuitively, before we actually describe the system, intuitively, what should this thing do? Well, if it has the minimum amount of energy, it should just stay at the bottom. And if you give it a little bit of energy, then it should vibrate like a pendulum does. But you should also be able to give it a sideways push. And so you could imagine that it rotates like this. Right? So it could be rotating along a circle like this. And then you should also imagine that if I give it enough energy, right, if I really hit it really hard, then it could go all the way up to the top and come back on the other side. And just, you could, if it was even fast enough, then it would just kind of rotate forever like this, right? Or you could imagine that I give it just, that I start it kind of upside down, right, at the very, very top, right? And it could be stable there. Well, actually, it's an unstable equilibrium point, but it's possible that for at least for a little bit of time that it would you could balance it so before it falls down. Okay, so I'm just trying to get, this is what the physical system really is. Okay, and so we're going to have a mathematical description of this thing. So what is the configuration space? Anyone?
S2?
Yeah, it's the two-dimensional sphere, which is the name S2. S2 is the set of points in R3. The sum of the xi squared is equal to 1. Okay, and what coordinates do we want to use for this system? Well, there's many choices, right? You may want to project down to the xy plane for some purposes and some regions. Maybe there's some subsets which will be useful to do it that way. Or you might want to use angular variables, theta and phi. There's all kinds of coordinates you could use. I don't care which ones we use. I'm going to use, well, we'll see what I'll use in a second. And then the phase space is the cotangent bundle of S2. So this will be, if I just describe it, in this case, it's kind of easy to describe. We can talk about points in R3, cross R3, where the norm squared of x is 1, and if I want to describe a tangent vector to the sphere, all I need to do is give a vector which is normal to the radius at that point. So I can say that the dot product x dot y is equal to 0. Okay, and this so you might say, well, okay, you didn't describe the cotangent space, you described the tangent space. You described the tangent vector y to the point x. So this is the condition for y to be tangent to the sphere at x. But the thing is that, as we know from linear algebra, when we have a dot product, when we have a symmetric, positive, definite, symmetric bilinear form, there's a natural isomorphism between a vector space and its dual. So it's not so crucial that I use the tangent or the cotangent space. Because of my dot product, they're basically the same. Okay, and what is the energy? The total energy. Yeah, so what is the total energy? Well, there's a kinetic term, and the kinetic term is always 1/2 times the mass times the velocity squared, according to physics. So this is going to be 1/2. I'll let the mass be 1. So it's the norm squared of the velocity. And then I need the gravitational potential energy. The gravitational potential energy is a linear function which is increasing as we go up. And in these coordinates, I might as well use x3. Sorry, this is not x cubed. It's the third coordinate, x3. And this is to be restricted. Yeah. So this is the energy function. This is the kinetic, and this is the potential. I'm not expecting you to know how to derive all this and it's not a physics class, but anyway, the function, you can see how it works. That this part of the function is a quadratic function on the cotangent space, on this momentum space. It does not depend on x, and this one is just the z component of x, of the position. Okay. Now, all right. There's another function that I want to point out, which I'll call L. I want to introduce this function, and it will be like this: x2, y1 minus x1, y2. All right, and if I look at this function, so using the Poisson bracket, this will give me some vector field. Okay, it will give me some infinitesimal symmetry. An infinitesimal motion, I should say. And which motion is it? We could use the formula. It's basically remember how it works, that the vector field generated by L is going to be like L bracket x1 times d by dx1 all the way to bracket L p3 d by d p3. Here I'm working on R3 cross R3. Okay, and if we work this out, then what you see is so L. So I'm just remembering what the Poisson bracket expression is, right? It's you differentiate the first function with respect to momentum first, and so L is going to be differentiated with respect to the y coordinate. The y coordinate is the momentum, so this will be dl dy1 times d x1 by dx1, and all the other terms will be 0 for that. And then we'll have d L, I think that's all that you have, because the second, in the expression for the bracket, there's only one possible way of differentiating x1 in such a way that that it will be non-zero. I have to differentiate it with respect to x1. So so if we work this out, we're going to get x2 d by dx1 minus x1 d by dx2. If we just work it out according to the formula. Okay, and so what do we see? Oh, I'm sorry, and there will be a p part. I think it will be p1 d by dp2 minus p2 d by dp1. You can check. I'm not sure about that. You can check the sign. So what is this saying? If we think of it inside inside three-dimensional space, you might recognize vector fields like this. So in R3, for example, or actually in R2, this is a two-dimensional vector field, right? It only involves x1 and x2. So if we look at the x1, x2 plane, a vector field like this would be like this.
I'm using the notation for p and y.
Oh, I'm sorry. This is y. Yeah, p is y. That's the coordinate I picked for p in the R3. Oh, I see what you're saying, that I did it many times. Yeah, sorry about that. Okay, so this is a rotational vector field. The standard rotational vector fields, they look like this, where you have x2 and x1. They always involve two coordinates, and they're always combined in this particular way. A d by db minus b d by dA. It gives you a rotational vector field. So what this thing is doing, this function, is the function that generates rotations about the z-axis. That's what's special about this function. This generates rotation about the z-axis, or the x3 axis. Okay, and we can see from the energy that the energy is invariant under that kind of motion, right? Because the energy only depends on the height. So so this is giving us a hint that that the energy is independent, is a kind of okay. So here's the main question that I want to answer. The question is, okay, let me just slow down. Sorry, I'm trying to rush too much because I'm looking at the clock, but it's better if I do this properly and not rush. So we have, so far we have H, the total energy, which dictates the motion of the pendulum. And we have L, the function which generates, this function has a name, It's called the x3 angular momentum. Function, which generates rotations about the x3 axis. Okay, so for example, if I had used, well, yeah, right, exactly. So now, when I look at the expression for the energy, I see that it only depends on x3, and so it appears that the energy will be unaffected by such rotations. And if I wanted to check that, we would like to know, the query is H invariant under such rotations? Okay, how would I determine, in other words, what is the derivative of H in the VL direction, right? This function L determines a vector field, right? And if I want to prove that this motion is a symmetry of the problem, a symmetry of the system, what I really want to check is that the energy is unchanged in this direction. Okay, and actually to compute this, I would like to take the partial derivative, like the directional derivative of H in the direction VL. But we know how to do this. We just take the Poisson bracket. Okay, so if we compute this, we see that actually this is so this is a computation using the definition of the Poisson bracket, and we get 0. That's the reason why I selected this particular function. It's because it's a function that Poisson brackets to 0 with H. So we have now we have number 1. So we have now 2 distinguished observables. So we have chosen 2 observables, which is a synonym for functions on phase space, and the term for this is Poisson commute. Okay, so that means that their Poisson bracket is 0. One of these, H, is special, is determining, determines the future motion, is the Hamiltonian. And so we can interpret this equation in 2 ways. So LH is equal to 0. This is the same equation as HL is equal to 0. And in this interpretation, I would say that L is preserved by the time evolution of the system. This expression I could interpret in the following way, that the energy is unchanged under x3 rotations. You see what I mean? That the same equation, right, is expressing the symmetry in 2 kind of equivalent ways. This second interpretation is particularly important because it's saying that L is conserved. In other words, the x3 component of the angular momentum is conserved. Okay? Is a certain function conserved under the evolution of the system? That question is determined by the Poisson bracket against the Hamiltonian. If you're interested in whether or not something is preserved by the evolution, what you do is take the Poisson bracket with the Hamiltonian. if you want to know, if yeah, I hope that that example is instructive about what's happening. So what's going on? So now we have the phase space has now two functions, h and L, which are actually preserved by the motion. Okay, so just remember what we were thinking about in the case of the simple harmonic oscillator. We had the phase space, it was just the xp plane, and we had a single function which was preserved. That function was the sum of x squared and p squared, and it gave us level sets, which are circles. Now I have the phase space of the sphere, the two-dimensional sphere. The phase space is actually four-dimensional because I have S2, that's two-dimensional, and I have the cotangent space to a point in S2, which it's two-dimensional as well. So it's a four-dimensional phase space. And on this four-dimensional phase space, I have two functions which are preserved. Well, that's pretty good because that means that the value, the common level set of these two functions, it must stay on the common level set. So that means that I can dimensionally reduce my problem, right? Just like before, right? I had a two-dimensional phase space and I had one-dimensional level sets, and I could conclude that my particle would just move around this circle. Okay. Similarly here, I have x1, x2, p1, p2, and I have some kind of, level sets of some other functions, h and L. So I would like to know somehow what these level sets are. It might help me to determine what the motion of the particle is in a kind of direct, more maybe indirect, but clever way. Okay, so this is what we say. Like we always tell people in the press, right? How do you think about higher dimensional manifolds? How do we study physical problems of high dimension? Well, we try to find conserved functions, and then we look at their level sets, which chop the problem down in dimension. Okay, so we're going to reduce the dimension by imposing that these quantities are conserved because we know that they're conserved. So let's to implement this strategy, this dimensional reduction strategy, we use what's called the energy momentum mapping. We put the conserved quantities together to define a map called J. And this will be the Hamiltonian and the x3 component of the angular momentum. This is a pair of functions which goes from the phase space to R2, because I have two functions. And let me draw the image of this function. Okay, so this is a very famous example. So I've seen this drawing many times. So what could the energy be? Well, the energy, depending on, the energy, the minimum energy is when it's not moving at all and it's just at the bottom. And that will be some minimum energy, H minimum. This is H and this is L. It's not important whether it's negative or positive. We just have to, decide what the minimum energy is. And it can be anything above that, right? I can keep putting energy into that thing by hitting it harder and harder. There's no upper bound on how much energy the spherical pendulum can have. But it cannot have anything to the left of that. And then what about the what about the angular momentum? Well, I can put angular momentum positive, or I can put angular momentum negative. But if I have a fixed amount of energy in the system, right? If I say that I only have a certain amount of strength, right? Energy, physical energy, right? And you're allowed to hit that thing however you like. There's an upper limit to how much angular momentum I can give it if I have a fixed amount of energy. So that means that for a fixed amount of energy, there will be an interval, and that interval will be bigger the more energy that I have. And in fact, that's what this thing looks like. It looks like this. It's not smooth at this point, but it's smooth elsewhere. And basically, this is the energy momentum region. It's this region here. This is what the system. These are the allowed values of the conserved quantities. Any questions about what I'm saying?
So yeah, I have a question. When you're defining this function j, so, as the domain being the cotangent bundle, space, if in this case, like, you know, we had like the cotangent bundle tensor or Cartesian product with the two sphere. So like if the two sphere is also two-dimensional and we're reducing by 2 dimensions, like is there an equivalent formulation of this where the domain of J is the two sphere and not the phase space?
Yeah, so there is a way of, absolutely, there is a way of, well, okay. Okay, I'm doing the analysis right now. To answer your question of dimensional reduction and so on, I am doing the analysis right now. So just pay attention to what I'm doing, and you'll get your answer. But you might want to ask it again after because the answer might not look like what you think it is. But anyway, we'll see. Hopefully, this will answer your question. So what is going on with this? So this means that if you set up the spherical pendulum somehow, so you push it in some way, and you let it go, and you let it behave according to the laws of motion, it will have a certain total energy, and it will have a certain z component of the angular momentum, and therefore it will be at a point on this diagram. Okay, but there are 4 coordinates on phase space, and you could say that 2 of them, L and H, are fixed, but there's some other directions, there's some other degrees of freedom where it's able to move. And so the way you should think is that the 4-dimensional phase space is being mapped to this blue region. Okay, but there's many points that are being mapped to this single orange point. That all those points that are being mapped are called the fiber, or the pre-image, inverse image, right? So the phase space is some high-dimensional space, right? Some space, and it's being mapped down to this region, this blue region. And the question that we have is, if I fix a point in this diagram, and if I look above, what is this thing? What is this 2-dimensional thing that I'm going to have here? Okay, because that is where the particle must be moving. All right. So, right. Okay, so let's try to analyze this briefly. So what should be the fiber at above this point? How many points in phase space should lie above that minimum energy point?
All of them? Because like
wait a second. So if you say all of them, that means all states have minimum energy. all possible states.
Oh, so if that's the case, then none of them, right? Because there's only one state which has the minimum energy.
So that means that how many states have minimum energy in this example?
One.
One. So there should be a single point. There should be a single point in phase space above this point. Okay? Does it make sense?
Yeah, yeah.
Okay, now what if I give it a little bit of energy, just a little bit of energy, but I say that there's no angular momentum? What kind of states correspond to that? If you start at the bottom, give it a little bit of energy, but don't give it any angular momentum.
There's going to be one dimension of points, like a regular pendulum, essentially.
So that means that it will move like this, let's say.
Yeah.
And so what are all the possible states? I mean, it could be at the bottom with a velocity, with a non-zero velocity.
Or it could be
up here with a slightly less velocity, or so on. And all of those have the same amount of energy, differing amounts of kinetic and potential, right? So there's all of those states. So okay, what about how many states are there with position pointing straight down?
2D of them, depending on the momentum coordinates.
Anyone else? Oh, so what I'm asking is, so we're at this point here. We're at this point. So I have a non-zero energy, and which is fixed, and I have no angular momentum. Okay, so that means that if the pendulum if the position of the pendulum is down, it has to have kinetic energy. So it has to have a velocity moving in one direction. In which direction must it be moving?
In the x3 direction? Is that what you mean? Like,
no, the pendulum is pointing down. It cannot be moving in the x3 direction. x3 is pointing up or down. We cannot have it, the rope is strong. It doesn't allow you to move in that direction. It can have a velocity this way, this way, this way, all of these different directions, right? So what are the possible velocity states if the position is at this point?
Like just R2.
Say it again, Kunal.
I wanted to ask a question.
You gave an answer though. What are the possible velocities if I'm at the red point and if the position is down?
Like R2?
No,
like
not R2.
A circle.
A circle.
There's a fixed speed, but any direction in the horizontal plane.
Yeah, that's right. So because the point is that if I increase that velocity, I'm adding energy, and the energy is fixed. The energy is non-zero, so the velocity has to be non-zero, but there's a fixed energy. Okay, so there will be a circle of vectors. Okay, but that's not the only states, because of course it may not be at the bottom. It might be, at some angle. And if it's at this angle, what are the possible, let's say that it's at a specific angle. So let's analyzing here. If the pendulum is like this, with, let's say this is energy 2, okay, then the possible velocities are pointing in a circle of directions. Okay, and so, but it may be that the pendulum is at a specific angle, and it still has this energy given by 2. But if it's at this angle, then what are the possible velocity states?
If the momentum is 0, wouldn't the velocity have to be 0?
So if the pendulum was like this at this angle, right, and if it had a velocity moving it around, then that would not be permitted because the angular momentum must be 0. But it may have a velocity moving it this way, right? I mean, one of the possible motions at fixed energy is just an oscillation in a plane. So therefore, it can have velocity this way. Okay, but it can also have velocity exactly in the opposite direction. So at this position, there are exactly 2 states above this red point number 2. All right. And this is true no matter at what angular position the thing is at. So in other words, there is a circle of possible positions now. You see, originally here, if it was at the bottom, there was no possibility for it to be in a different position. It has to be at the bottom. And the velocity is a possible circle. But in this case, the position is a possible circle. But at each position, there are 2 possible velocities. So what that means is that I actually have 2 circles. Okay, and that is true up until, for this fixed for this fixed position of energy and momentum, right? I can increase this angle up to a certain point, theta max, and at that point it will have the maximum potential energy for this amount of energy, the amount of energy of the red dot that I'm fixing, right? I'm fixing the energy. Remember that the whole analysis is happening at a fixed angular momentum and a fixed energy. And I'm trying to analyze all the possible states. So I'm drawing the states in, let's say in purple. These are all possible velocity states. And here I have 2 circles, one corresponding to each choice of the velocity state at that angular position. And then I have a maximum angular position, in which case the velocity must be 0. It must be that it's at the height, at the top of the oscillation, at this point of the oscillation where the velocity is 0. 0, 0. Velocity is 0. And that can happen at a circle of possible positions. Okay, so what I've done is I've analyzed the possible states at this energy and momentum by slicing it via angle. I'm looking at it, I'm sweeping through the possible angles, and I'm saying at 0 angle, there's a circle of possible states, and at a small angle, there's 2 circles of possible states, and at the maximum energy, at the maximum angle, there's a circle again. So what does that mean? That means that depending on the angle, I start with a circle of possible states. I become 2 circles intermediate. And at the top, I have 1 circle. So if I put all of these together, what you're getting is a torus, which is being sliced horizontally. Does it make sense? So let me just move this out of the way. The answer is that above this point in phase space is a 2-dimensional torus. And above all these points, it turns out, we have a 2-dimensional torus in the phase space. Okay, except what happens at the edge points, at the boundary points, what happens is that the spherical pendulum is moving like this. It's moving with maximum angular momentum for a fixed energy. And so that means that it's inclined at a certain angle, and it's just moving in a circle. It's not oscillating at all in the angle. It's at a fixed angle. It's just moving around like this. Okay. And so the possible states above this point is just, it turns out to be just a circle. So what is generically a two-dimensional torus squishes down at the boundary to become a circle. At this point, remember, it was just a single point above this point. And then there is a very special point. There's a special point. I don't remember. I think it's, yeah, there's a special point here somewhere, which depends on the size of the sphere, where what happens, I mean, this is just for your information, it's not in this class really. The fiber turns out to be a singular torus, which looks like this, a pinched torus. Okay, so there's only one fiber, which is exactly like that. And there's a special point on that fiber, this point, the singular point, and that's a special state. And that's the state where the pendulum, it's the unstable equilibrium at the top. Which in principle, it would just stay there forever. If you were in that state, it would evolve by doing nothing. Okay, so what is the meaning of this? So like, I mean, what is so great about this? Well, it's very similar to the oscillator that we studied, right? When we were studying the oscillator, we saw that the energy function cut the phase space into circles, and then therefore the motion of the oscillator must preserve the energy, and so it must stay on one of those circles, on one of those level sets. Well, here it's the same thing. What we found was the Hamiltonian function, and we found another function which Poisson commutes with the Hamiltonian. And as a result, both of those functions will be preserved by the evolution of the system, and therefore the state must remain on a level set of both functions, and therefore it must remain on one of these tori. So we conclude from this that the system must remain on the level sets of H and J, i.e., it must evolve on a torus generically. As long as we stay away from these particular special states. The special states are this state, and these states at the boundary are special. Okay, and what is this torus? Let me draw the T2 like this, the torus. And so basically, let's see if I can draw a picture of this. So, yeah, this is just for your own information. At the end of today's class, I just wanted to give you a kind of a picture of what's going on. So so on this torus, on this level set, there are two vector fields. VL and VH. Okay, and the VL is basically a symmetry. This is a rotational symmetry. Whereas VH is the evolution in time. The rotational symmetry on a torus, you may not be surprised that it's just rotating the torus. So the rotational symmetry is just rotating the torus like this. And the other thing is a vector field at some angle. And so if we start at a point here and we find an integral curve, that integral curve is going to be a curve on the torus. It's going to do this. Okay. And these curves, if I try to draw them, they're going to be things like this. So if this is the sphere, and the pendulum, the pendulum is moving on the sphere. If we project this trajectory in the torus down to the configuration space, which is the sphere, then what we'll find is it'll be doing this. It'll be oscillating. See what I'm saying? It'll be oscillating like this, and it may not return exactly to the exact same position because of the fact that this direction inside the torus, it may be irrational, and so it may never really return to exactly the same state. Okay, and it'll go in this way, in this band on the sphere. So what I'm trying to I'm trying to give you an idea of how these classical mechanical systems are analyzed. The way that they're analyzed is that you're trying to find other functions which commute with the Hamiltonian. And the reason, which Poisson commute with the Hamiltonian. And the reason for that is because it allows you to reduce the analysis of the problem to a level set. And you may use the geometry of that level set to understand some qualitative aspects of how the system behaves. Okay. And all of this has a direct analog. It's exactly the same in the quantum mechanical case, that we're going to have a particular operator which governs the time evolution of the system, and we're going to be looking for other operators which commute with that operator in order to simplify the analysis of the problem. That's how we're going to do the Schrodinger equation on the line, the hydrogen atom, all of these things. So it's the kind of sequence of the logic of the thought is exactly the same. Okay, I'll leave it there. Next week, we're going to start with the axioms of quantum mechanics. So we're really starting with the quantum version of all this stuff. And actually, for those people who are freaked out by all this coordinates and manifold stuff, you'll be glad to know that one of the great things about quantum mechanics is that it's all about vector spaces. So you don't see anything about manifolds. Once we transfer to the quantum mechanics, it's there's no more coordinates. Oh, I just saw a cat.
Yeah, my cat is occupying my writing tablet right now. Yes, if it's distracting, I can turn off the video, but I just...
No, you should have the video only about the cat. It would be great.
Yeah.
Okay, everyone, have a good weekend. Any questions?
I have a quick question.
Yeah, go ahead.
So I actually have two quick questions. The first one is, does a geometric structure on, let's say, the phase space ever matter?
What do you mean? What is a
Say,
geometric structure?
or metric? Because we've been only working with smooth structures. So it seems that the geometry doesn't really matter to the Hamiltonian analysis.
What do you mean by geometry? Sorry.
So
Are you
for
talking
example,
about having a Riemannian metric?
Things like that.
So, I mean, a symplectic structure is a geometric structure. Any kind of tensor, any kind of tensorial structure on your space is a geometric structure. But you're talking about a Riemannian metric in particular.
Yeah.
I would say that you could think of it this way, that okay, so I would phrase it in the following way, right? What is a Riemannian metric? A Riemannian metric is a way of measuring the size of tangent vectors. Okay, it's a norm. It's a dot product on tangent vectors. That's what it is, right? So that means that it's you could think of it as a quadratic form on the tangent space. Okay, so what is a quadratic form on the tangent space? It's a function. It's a quadratic function on the tangent space. Do you agree with what I'm saying?
Yeah, that makes sense.
So the Riemannian metric, you could think of it as a quadratic form, which is just a function on the tangent spaces. On every tangent space, you define a quadratic function. That is what a Riemannian metric is. So what does that mean? That means that a Riemannian metric on the configuration space defines a function on the phase space. And that function is the function that measures the size of these vectors, of these tangent or cotangent vectors. What do we normally call that function? That function which measures the size of the momentum, the size of the velocity, the norm squared of the velocity. What is the name of that function usually?
Speed.
No. The norm squared of the velocity.
Energy?
It's the
kinetic energy.
It's the kinetic energy. So a Riemannian metric on the configuration space is the kinetic energy of the system, which is a function on phase space, which is part of the Hamiltonian. So the role that a Riemannian metric on configuration space plays, because we know, like in reality, whenever we have a configuration space like a sphere in our actual physical space, there is a way of measuring distance. And so there is a way of measuring the size of those velocity vectors. So we do have a Riemannian metric whenever the configuration space is somehow related to physical space. We know that we have a Riemannian metric there. And that Riemannian metric is a function on phase space. It is the kinetic energy.
I see.
That's so it's they don't tell you this type of thing.
Cool. I have to write it down.
In the physics department, they won't tell you.
I have one more small question. This one's smaller. Is if we want to learn more about the classical mechanics that we just talked about, where should we do it? Because the textbook, I realized there are some books that has the beginning of the chapter on it, but are those the best place to learn about it?
Well, I mean, you should take a course on classical mechanics if you really want to learn about it. But one place that you could learn about it in a good way is there's a book called Geometry of Physics by Theodor Frankl. And that's where you should read about it. He'll tell you what the real mathematical models are that physicists have been telling you about. All of these theories, all of these physics theories, they're all mathematical models. They involve mathematical structures. So you should learn, what those structures are.
I see. Thank you so much.
You're welcome. Okay, everyone, have a good weekend. Oh, Jai has another question. Okay, go on.
Yeah, can you just quickly go over why there's the two circles at the angle theta? Like I understand the circles of the velocity at a single point, but then
So do you understand that we're analyzing all states that have a fixed amount of energy and a fixed amount of angular momentum, right?
Yeah.
So if we're analyzing all those states will have varying angular position, right?
Yeah.
That angular position could be 0 or it could be a certain angle theta, and there is a maximum, right? So you're asking about what happens if theta is intermediate between the maximum and the minimum, right?
Yeah.
So if you're at that position, that means that some of your energy is kinetic.
And some is potential, yeah.
Because you're not at the highest possible angle. So some of your energy is kinetic. That means that you've got to have a non-zero velocity, right?
Yeah.
You have to have a certain amount of velocity squared. But where can that velocity possibly be? It could be either, if this is the curvature of the sphere, it could either be in this direction, moving around the sphere, but that is impossible. That is not permitted because you're not allowed having any angular velocity. It has to be along the sphere in this way. It has to be moving up or down. Okay, and that is true. So you could have any velocity, but it has to be moving up or down, and it has to have a fixed norm squared. So it has to be either positive or negative at the same norm.
Oh, and that defines the two circles. Okay.
That means you're going to have one point at this angle, but of course at every angle around the sphere there is such a state.
Yes.
There's a state of a velocity moving like this. I don't know, if I had to draw it, I would draw. If I had to draw it, I would say that there's a theta max and then 0. And then if we have some intermediate theta, I could have a state like this. So let me draw. These are all states at the same theta. And for each one of them, I could have a velocity which is fixed. Right? And they form together a circle. But they could also have the opposite velocity. They have the same norm squared. They'd be moving this way. Same magnitude, just different direction. And they form another circle.
Oh, so it's two in that sense. Okay.
Yeah.
Thank you.
And of course, you can see that if you're at theta max, these two circles become one circle. And then if you're at theta min, the circles, you still have a circle, but the circle is different. It's a circle of all different
velocities. Yeah.
Okay, Bernie, you're really blowing up these days on social media.
Okay. So I have a question on law of aggregate system.
Yeah.
So is that like a axiom, or is that derived?
It's an axiom, really. The axiom really is saying that if you have two non-interacting systems, then the Hamiltonian system is a Cartesian product, and the energy is a sum of two components, one from each product factor.
And does that axiom come from the intuition of a physicist, say?
Well,
I mean, it just seems so out of nowhere.
Well, no, it's not out of nowhere, because if you have two systems which are non-interacting, you know, that what that means is that the mathematical model, you know, there has to be a complete self-contained model for one of the systems and a complete self-contained model for the other. And if you just have the two models independent from each other, the mathematical way of combining it in such a way that it doesn't do anything is Cartesian product, right? So it's a consequence of the fact that the mathematical model also has the notion of independence, that you can, for example, if you take a Cartesian product of two systems, then the solutions will be Cartesian products. And therefore, what that means is that you don't need to solve them jointly. You could solve one, solve the other, and then take the product of the solutions. So because the mathematical model has this independence, namely that the solutions are product solutions, and because we know that the physical systems are independent, that means that the mathematical model has the same behavior as the physical systems. That there's a way of combining them without interaction. So I don't know. I guess the point is that if you were looking for a mathematical model for this physical system, it would have to have this ability of being able to combine systems in a non-interacting way. And the Hamiltonian model has that property, namely Cartesian product.
So I'm convinced for the Cartesian product part, but what about the Hamiltonian function? There are a lot of ways to combine Hamiltonians, right?
No, I disagree. I mean, if you have a function on x and a function on y, and then you take x cross y, how are you going to produce a function on x cross y? I mean, you could. What I'm saying is that there's not that many ways to do it. There's certainly this way, but the argument really is this: that if you look at how the Hamiltonian formalism works, when you take the sum, what happens is that the vector becomes the sum of the two vectors. Okay, and what that means is that you have a product, and then you have a vector, which is the sum of a vector on the first product factor and a vector on the second product factor. So when you evolve along that sum vector, what's really happening is that the x component is evolving along the x component vector, and the y component is evolving along the y component, and they're independent. It's just that when you're taking the Cartesian product, they go together. So yeah, if you think about how the thing works, the way it's designed is so that you can combine them in this way that one doesn't affect the other. But the amazing thing is that even though you're doing a silly thing where you're just combining by taking products, you're opening up a huge amount of possibility, because now you can introduce functions which you didn't have access to before, and those functions will let the two particles interact. And so it's a kind of remarkable that without knowing anything about the physics of how particles might interact, you can just look at the Hamiltonian system and you can see what simple functions you may introduce that would introduce interactions. And it turns out that those simple functions tend to be the ones that physics uses. It tends to use the simple products or simple ways of combining the two factors. Okay, I've talked enough. I didn't take a break. I'm sorry, I should have taken a break. I didn't realize.
And just quickly, like for the velocities that we have in the circles, like in the intermediate angles, right?
Yeah.
Like they have to be in the y3 or minus y3 direction, like x3 or minus x3, because otherwise L is not going to be conserved, right?
Correct.
Because
L is not going to be zero, not conserved, but zero, because I picked a point with L0.
Oh, okay.
Remember here, this point here.
Yeah.
Was picked so that L was zero. That's the reason. Yeah. Okay. Have a good weekend.